So I have some heading on the screen for you which says periodic motion. So the way I introduce the chapter to the children, see in this 11th standard, when we are talking about oscillations, we actually more specifically teach them about simple harmonic motion, right? That's the kind of oscillatory motion that we are going to be teaching in our 11th standard level to children. So to bring in that simple harmonic motion concept, first of all, they should know some basic motions. And in that, the very first thing that we have here is periodic motion. You can see the heading there. Now, what is this periodic motion? I generally give children two examples for period. What do you think is periodic? The sentence is there on your screen. Often a physical system will repeat the same motion over and over. We call this periodic motion or an oscillation, it says. I would like to correct it a little. Now, when you have, say, I give them two examples and I ask them to give me the similarity and difference. Something similarly I gave you the other day also. I always like doing that. Say, for example, the motion of, say, the earth around the sun or the moon around the earth. That's one example I'll give you. The other example I give to the children is the motion of a simple pendulum that they generally have definitely seen in their lower classes. They would have found out the time period of a simple pendulum and all that. So I give them these two examples and I ask them to give me the similarity between the two motions and the difference in the two motions. So what do you think is the same for both? And what is different for both?
Repetition is same.
Repetition. Exactly. After a regular interval of time, right? After a regular interval of time or period of time, the motion gets repeated. Isn't it? Say if I take the earth going around the sun, once in how many days does it repeat its motion? How much time does it take to go around the sun once, our earth? 365 days. Then again, it's going to repeat its motion the same way, right? Likewise, I could talk about all the planets going around the sun or the satellites going around the planets. All these are motions where the motion is getting repeated after regular intervals of time. Then what about my simple pendulum? If I have a simple pendulum, what about the simple pendulum?
Same way, ma'am. Periodically, it reaches the
exactly. Even in simple pendulum, like if I can just take 1 second, give me a second. So if I can draw a simple pendulum, right? And if I want to just pull it to one side and leave it, what happens? I just let go. Definitely, this is going to come back here. Then is it going to stop here? I just let go the simple pendulum. Will it stop at this position or will it overshoot, go that side? Then again come back. Does this motion happen? And it repeats itself after regular intervals of time. This again. So what is same between the two is, that is between the earth going around the sun and this pendulum oscillating or the pendulum moving or the motion of the pendulum. The similarity is that both of their motions get repeated after regular intervals of time. Hence, we say these kind of motions where they get repeated after regular intervals of time, we call it as, or we define it as, what, teachers? We define it as periodic motion. So are we clear? So periodic, that is where I start off. I start off with this term called periodic motion. So periodic motion is a motion, or we say an object is in periodic motion whenever its motion gets repeated after regular intervals of time. Repeated na anartham. It has to go the same way that it went earlier. So Earth starts from a point, it goes around, comes to the same point, again it repeats its motion. Similarly, pendulum, if you take, yes, it oscillates like this. So you can see my finger, it oscillates like this, right? So it starts from here, it goes to the mean position, then goes to the other side, then comes to the mean position. Again, it repeats its motion always. So at regular intervals of time. So this we can define it as periodic motion. So just by giving these two examples where there is similarity, now what is the difference between the two? Similarity is they repeat their motion regularly. Ilya? After a particular interval of time, yes, they go the same way. What is the difference between the two motions? ரெண்டுத்துக்குமான வித்தியாசம் என்ன?
Here goes circular motion, ma'am.
Exactly. One, like, it goes in a circular path like that. It doesn't again go back like this, right? It goes only in one direction, west to east. Its direction is like that. It doesn't stop and then turn back and go like that, does it? No. That is the way the earth goes around the sun. But what about my simple pendulum?
It cross always mean position.
Exactly. It goes in one direction, comes back to a particular where it rested, it comes back, comes there, then goes in the other direction, then comes back. So it is, the difference is, in the first example that I gave, it simply goes in that elliptical path in one particular direction, whereas here it has a to and fro motion, right? So that's a difference between the two examples that I have given. But both are periodic motions. Now we can introduce what is known as oscillatory motion. What is oscillatory motion? It's a periodic motion where the object has a to and fro motion. Yes, teachers.
Yes, ma'am. We can
That's
say special type of periodic motion.
It's a special type of periodic motion where the object undergoes a to and fro motion about a position called mean position, right? So that's how I introduce the chapter. Hopefully I'll also introduce it that way. It would be nice for them to understand what is periodic motion, what is oscillatory motion. Then there's one very often asked question in this part of the lesson, in the very introductory part of the lesson. The question very often asked is this. So maybe I'll put it in my PPT. The question is this. So see if you can justify it. So I'll keep switching from here to there to here. So suppose a question asks, the question very often asked CBSE question is this. That is, all oscillatory motions, okay, all oscillatory motions are periodic. Will you agree?
Yes, ma'am. Correct. Absolutely correct.
Definitely, absolutely fine. All oscillatory motions are periodic. But all periodic motions
Are not oscillatory.
are not oscillatory. Are we agreeable on this sentence?
Yes, ma'am.
Yes, ma'am.
Why are we agreeable on this
Yes, ma'am.
sentence? Why are we agreeable on this sentence? Why do you think we agree on that? How do you agree on that? How do you justify it? The question would be justify. All oscillatory motions are periodic, but all periodic motions are not oscillatory. So this is one basic question that often is asked in the CBSE 11th part. Are not oscillatory, justify. So how do you justify? How do you think you can justify this statement? You must justify this statement. How do you justify this statement?
Ma'am, even circular motion is periodic if in the case of.
So the best way to do is give two examples. Ask children to, you have given two examples now. We discussed two examples now.
Yes,
We
ma'am.
discussed the Earth's motion around the sun, and we discussed the motion of the simple pendulum. And we do know both are periodic. But then one is a to and fro motion, which we call oscillatory. The other one is not, isn't it? So the best way to answer this question would be is to give two examples like this and ask them to explain this statement. Fine, teachers. Yes. And then we move on into what is known as simple harmonic motion. Now, what is simple harmonic motion? What do you think? How do we define simple harmonic motion, or where do we start to explain this simple harmonic motion? What example do you take generally to introduce this simple harmonic motion? A very simple example that I take generally. again is a simple pendulum. Right? Okay, so if I take a simple pendulum, so this is easy for the children to visualize because they've already seen a simple pendulum. Anything else you try to explain with, they don't get it that easily according to me. But then if you have some other things where you have beautifully explained, you could share it so that I could also use it here. Yes, teachers. So what I do is I take this simple pendulum. Okay, again I ask them, you pull it to one side and you leave it. Isn't it? And if you let go, what happens? This keeps oscillating. And I can at another time draw the diagram here. So this oscillatory motion keeps happening. Now what I ask them is, suppose I want to displace this bob a little further. Should I use more force or less force? Say I want to pull it to this place. Should I use more force or less force?
Less force.
Less force? If I want to pull it more, sir, should I use less force or more force? I want to cause a greater displacement.
We have
So
to
do
apply
I-
more. We have to apply more force.
more force. We
More
have to
force.
apply more force,
Yes.
right?
Yes, ma'am.
More the displacement from the mean position. So the more this x increases. So this is x1 and this is x2. For which will I use a greater force? For a displacement of x1 or x2? Definitely, children can very logically say it will be more force to take it to x2 than to x1. So which tells me this statement, right? So from the example, you can bring this statement that the force required to cause the displacement will be proportional to the displacement. Okay, fine. Does this alone define simple harmonic motion? Is it enough for me to say that force is proportional to displacement? Then it will be a simple harmonic motion. There's something else also. There is something else also that we should bring in.
Acceleration.
Acceleration. What can we say about acceleration, sir? So if I say force is proportional to x, then automatically you will say A is also proportional to x. Why? Because my F is equal to m times A, right? F is equal to m times A. So if F is proportional to x, then A should also be proportional to x. Okay, is this enough again still to say this is a simple harmonic motion? Is there any other special feature which says that this is a simple harmonic motion? So now this is what I was drawing. So now you have the simple pendulum. I pulled it to one side, right? And then if I wanted to take a greater displacement, definitely I need a greater force. This is what we were discussing. So we said F is proportional to x and A is proportional to x automatically because F is m times A. So definitely A should be proportional to x. Are we still missing something? Is this fully defining my simple harmonic motion? Am I
Force
missing?
and the displacement opposite in direction, so that negative
Exactly. So what is this force that we are talking about? See,
Restoring force.
when you exactly. So the force that you apply to cause this displacement is the applied force. Right? Is the applied force. You're applying the force to cause that displacement. But if you leave it there, it's coming back, isn't it? If you
Yes,
leave it
ma'am.
here, does it stay here? So my cursor is there. If I keep it at this point, does the bob stay there or does it come back here? And then go back on the other side. So it does come back, right? So if it is coming back, there should be some force that is bringing it back. Otherwise, it cannot come back, right?
Yes, ma'am. Restoring
So,
force.
Exactly. So here we start talking about restoring force. So that restoring force. So now if this force is proportional to x, the more the greater force that you apply to cause a greater displacement, the restoring force also is proportional to x, because only then it can bring it back. Otherwise, it can't bring it back, right? So the restoring, so the important point here for your simple harmonic motion is that force, this restoring force is proportional to x, but then minus x. Why minus x? Why that minus
Displacement is
comes in?
opposite direction, ma'am.
Exactly. See, why? Because see, when I am displacing it this way, and when I just leave it, it comes back in this way. It comes back in this direction. Will you agree? it'll come back in this direction, right? Which
Yes.
means whenever I cause the displacement in one direction, there is a restoring force happening in the opposite direction. So here the feature is the restoring force is always opposite or in a direction opposite to the direction of displacement. And that restoring force is proportional to the displacement I'm causing. Then I say the oscillatory motion is a simple harmonic motion. So that's the main important point. Similarly, A will be proportional to minus X. Then I say it is a simple harmonic motion. If it is not minus, then it can simply, I can push the object like this and keep making it move in that particular direction itself. Then it becomes a translatory motion. Are we clear, teachers?
Yes.
So very important to tell when we are discussing simple harmonic motion that yes, F is proportional to X, but F is proportional to minus X. What is that F? It is a restoring force. What is that X? It's a displacement that is being caused by the applied force. Are we clear with this?
Yes, ma'am.
Yeah, are we
Yes,
clear with
ma'am.
this? Fine. So this is the very first
Yes, ma'am.
introductory part that I would do by simply taking an example of a simple pendulum. Fine, teachers. So hopefully you also do the same. Or do you have any other method where you explain the simple harmonic motion? And one more, the next thing that I do is after this, okay, maybe I can move on. The next thing that I do is I call the diagram that I'm going to show you as the motherboard diagram. The computers like you motherboard அப்படின்னு சொல்லுவா இல்லையா? That is the main part without which the computer doesn't work or the computer doesn't understand how to work. So similarly here, what I always tell them is what we are going to do now. I tell them what I'm going to do now is the motherboard diagram. Why? Because if I understand this diagram and if I understand how things work in this diagram, my oscillations chapter and waves chapter basic is done. We understand this part beautifully, then everything, most of the equations that we write or the derivations that we derive or the expressions that we write for the three basic quantities, namely displacement, velocity and acceleration in simple harmonic motion, or the displacement equation that we write for a plane progressive wave, everything is beautifully understood if we understand this. What is that you think? I'm going to show you after getting some answers from you. After explaining about simple harmonic motion, what is the next topic that you teach? From where do you derive the expressions for the displacement, velocity, and acceleration of a simple harmonic motion? You do something, isn't it? Do you do something called projection of a uniform circular motion on its diameter?
Yes, ma'am.
Do you people do that? Because that
Yes, ma'am.
is the what do you call that is the diagram, that is the explanation, or that part is the most important part. If you can make them understand that part, everything is done. Even in waves, the phase difference between two waves or the phase difference between two particles, everything can be beautifully understood by making them redraw this diagram again and again and making them understand that. So let me see, I'll try to do that here for you. See how useful it is. Can we? So we all know what is uniform circular motion. We all know that, isn't it? Uniform circular motion is one where the body undergoes circular motion. So the body undergoes circular motion. So I'll try drawing a circle. Let me see if I am not bad. So the body is undergoing a circular path, or it is traveling in a circular path where only the magnitude of its velocity remains constant, but the direction keeps changing continuously, right? The magnitude of velocity remains constant. That is called uniform circular motion, isn't it?
Yes.
Okay, now one question I have regarding this. If I say uniform circular, somebody's got something? You were trying to ask something? No? Okay, can I proceed?
Yes, ma'am.
Yes. Okay. Now, what is uniform circular motion, or which, I mean, like when you take uniform circular motion, we say the magnitude of velocity remains constant. In which plane do you think it should be? Horizontal plane or vertical plane? When I teach this, I give two examples again. I almost, for all of my chapters, whenever I start off with anything, I always try to pick from everyday examples. The two things that I pick here for circular motion is, one is merry-go-round. Rangaratnam, porole. Okay, that one is one I choose. The other one is giant wheel. Both are circular motions.
Yes, ma'am.
Both are circular motions. Which is uniform and which is non-uniform? Do you think both are uniform motions? Or one is uniform and the other should be always non-uniform? Any idea?
I think both are uniform or circular motion, ma'am.
Both are uniform circular motion. Let us try and understand that. Okay. Now, when I go in this merry-go-round, okay, like this I go, isn't it? In the horizontal plane. Correct?
Yes, ma'am.
Right? Fine. Now here, by rotating that thing, I can have the velocity's magnitude to be the same when it goes like this. And the gravitational force acting at every point, is it the same or different?
Same, ma'am.
Same.
Because the height is
M
same
into
only.
G. Exactly. Height
Yes,
is
ma'am.
same only. M into G is the same. M doesn't change. G doesn't stand at that height. So M into G is the same, right? So it is not
ma'am.
going to alter my velocity in any way. Correct? But what
Yes.
happens if when you go in a merry-go-round? Do you think effect of gravity will come in?
Merry-go-round or giant wheel, ma'am, you're asking?
No, sorry, in the giant wheel.
Giant wheel height is different, ma'am, so that gravity will change, ma'am.
Gravity will change. So if the gravitational force changes and I'm going to move up, while moving up, I'm going to move against the gravitational field.
Of course.
So will my
ma'am.
velocity decrease or increase?
Velocity decrease, ma'am.
Definitely velocity will decrease, right?
Yes, ma'am.
So it's very difficult to have a uniform motion in the vertical
Yes, ma'am.
circle, right? When we do
Yes,
in the
ma'am.
later class in work for energy in vertical circular motion, we do show that the velocity decreases, reaches a minimum value at the top, and then it comes down, it increases and reaches back its velocity at the lowermost point, isn't it?
Yes, ma'am.
So now here we are choosing uniform circular motion. So let us understand it is on a horizontal plane. Fine.
Yes, ma'am.
Now,
Yes,
when I
ma'am.
take this uniform circular motion, so let us come back to our oscillation chapter. Okay. So what we are going to do here is projection. And have we done in dot product? So you'll have to be able to connect all the topics wherever it is to be integrated. We should be able to connect it, right? Have we done in dot product something called projection of A vector on B vector and B vector on A vector? Are you familiar with that part? Say po A dot B பண்றோம்னு வெச்சுக்கோங்களேன். Okay, we write it as
AB cos theta.
exact. That's what we write it as AB cos theta. Correct? And how we actually discuss this is like this. So if we can put all these things into in place first, then understanding these parts are very easy. So I have an A vector. I have a B vector. Okay. And I'm saying the angle between them is theta. And I say A dot B is AB cos theta. So can now what I want you to do is, this is A vector, right? So can I resolve this A vector into two? One along this direction and one along this direction. This is resolution of vector. Ilya, or vector undana, I can split it into two parts, right? And if this is theta, what is this? Cos theta or sin theta? This is cos theta component, and this is and this is sin theta component.
Sin
Correct?
theta.
Okay. Now we are saying A dot B is AB cos theta. Correct?
Yes, ma'am.
Is AB cos theta. This is what we say. Now can I see this AB cos theta as B into A cos theta? Max le adin thirpi இப்படி எழுதலாம் தானே? A into B into cos theta is equal to B into A into cos theta. எழுதலாம் தானே?
Yes, ma'am.
Okay. Appo what is this A cos theta actually? So if I have a B vector here, if I have let me choose another color. If I have a B vector here, I have a B vector. I have an A vector here, which I've resolved into A cos theta and A sin theta. Now I call this A cos theta as projection of A vector on B vector. Are we clear with this? What do we call this A cos theta? We call it as projection of A vector on B vector. Fine. So now coming back to what we were discussing here, we are in the oscillatory motion chapter, isn't it? So here what we are going to do is take a particle which is undergoing uniform circular motion, then have a coordinate axis like this. Okay. Okay. Now, again for this also, explaining this also, I go back to my pendulum. All right. Sorry about the diagrams, but we should kind of, hopefully you will excuse me for that bad diagram, but then we'll understand the concept. Say the pendulum is starting from the mean position. All right. Pendulum is starting from the mean position. So I'll take that as a particle and place it here. But I want this to undergo circular motion. Okay. Are we getting this? So I'm starting from the mean position. So this is my origin. So I place the particle at this point. Now this particle, which is at P, is after some time, say it is going to go in a circular path this way. Then after a time T, it will reach here. Somewhere here it will reach.
Yes, ma'am.
It would have covered an angle theta. What is this OP dash? Can I call it as a position vector of that particle? That OP dash, can I call it as a position vector? That is what always from the origin to that
Yes,
position
ma'am.
where the particles, if I draw an arrow, that's called position vector. Fine. Can I resolve this position vector into two components? Like the way I resolved A here as A cos theta and A sin theta. Can I resolve that? I can, isn't it? Can I or can I not?
Yes, ma'am.
I can. Okay. So one will be along this OP, the other one will be along this. So one will be along the x-axis OX, the other one will be along OY. Right?
Yes, ma'am.
Now what I want you to do now is bring the P dash back to P.
Yes.
Okay. Bring the P dash back to P. Okay. Or before that. Now if I resolve this OP dash, so let me use some other color here. That's the thing of online nothing, or you use different color chalk pieces. This is what I do in class. I use different color chalk pieces to show them. So now this OP dash can be resolved into two components. One I've shown you with the yellow. That's the what theta component? Cos theta or sin theta?
Cos theta.
Cos theta component, right? Thank you, sir.
Cos theta.
Cos theta component. And the other one, if I can draw, this is going to be sin
Sin
theta component. Pakka?
Yes.
Okay, now what I want you to do. So you know this is A cos theta and this is A sin theta. Now what I tell the children is bring the P dash to P. What has happened to A sin theta? P dash P க்கு வந்துருச்சுன்னா, you have only the yellow vector, correct? There's no angle, no.
It reached to O.
It has reached to, so what has happened is that A sin theta has become 0. So where is that A sin theta sitting? Sitting at O.
O.
Are we clear?
Yes.
Are we clear? Then now you again start moving P. When it is at P dash, where is my A sin theta? At some point here, which is N. Now, if this P dash comes to Y, if this particle comes to Y, where is my A sin theta? This only vertical component I'll have. Yellow இருக்கவே இருக்காது, correcta?
Only A sin theta.
Only A sin theta. Now, okay, let this particle come to this point. Now, what has happened to my A sin theta again? This yellow one, puriyarda? Am I reaching you people?
Yeah, ma'am.
The yellow will be on this side now instead of that side.
Yes, ma'am.
But this A sin theta would have again become 0. Now let the particle come here. When the particle comes here, what happens? When the particle comes here, what happens? Again, this A sin theta is on the other side. Yellow is gone. Correct?
Yes, ma'am.
Again, when the particle comes back to P, yellow comes back to the same original direction. But sin theta has become 0. Are we clear?
Yes, clear, ma'am.
Are we clear? So now I just told you that A cos theta can be called as the projection. Similarly, A sin theta can also be called the projection. So now what we are trying to understand here is this A sine theta, or the projection of this uniform circular motion on a diameter. We are doing it on a diameter, right?
Yes.
Correct? And the X and Y that I've drawn there is the diameter of that particular circular motion. What you see is that projection is having a to and fro motion. Agreed?
Correct, ma'am.
To and fro motion. And as it is moving, the to and fro motion, the amplitude or the displacement depends on how much you're taking it through. And also, if you see one more thing that you have to say for simple harmonic motion, you said F is proportional to minus X, A is proportional to minus X automatically. And one more thing that I want to know, when you're allowing it to oscillate, when you're allowing the pendulum to oscillate, at least for a few oscillations, or இடத்துல போய் நின்னுட்டு it will turn back, then it will go on the other side for the same. You agree? At least for the first few oscillations. Later on, damping happens, so slowly the amplitude or the displacement will start decreasing. But at least for the first, it will go through the same displacement. Correct? That means it will be taking the same time to repeat its motion. Will you agree?
Right.
So it will be an oscillatory motion of one single time period. And if the time period is constant, then the frequency will also be constant, because frequency is 1 by time period. So all these conditions will be satisfied for your simple harmonic motion. 1, restoring force proportional to X and opposite to X. 2, acceleration proportional to X and opposite to X. 3, time period is a single time period or a constant time period. 4, the frequency is also a constant. And also for the first few oscillations, this maximum displacement that it undergoes will be a constant. That means that maximum displacement, you define it as amplitude. So the amplitude will also be a constant. So all these will be satisfied for a simple harmonic motion. Pakka? So on the idea, then I go here. So now here what has happened in this projection? I am getting same amplitude on either side, and the motion repeat itself. Now once it is reached here, the particle has finished one complete circle. Again it will repeat its motion, right? That means this projection also will repeat itself. That means, is it repeating after periodic intervals? Yes. So this projection of this uniform circular motion is a simple harmonic motion. This is the first thing that you have to drive. Hopefully I am clear, and hopefully you have got me. Is it fine? So I'll show you a nice GIF that I got. See that. So can you see the projection oscillating up and down when the particle is moving in a circular path? The black is the particle. Hopefully you are able to see. The black dot is the particle that is undergoing circular motion, whereas the red dot is a projection, the sine theta projection that we are talking about. Fine, teachers. Are we getting it?
We are able to see.
As you are able to see. So is it fine? So can I move on?
Yes, ma'am.
Okay. Now next thing for us, for any motion, what are the 3 basic quantities that we have to give? What do you think are the 3 basic quantities? Displacement, velocity, and acceleration. And we need to derive an expression for these 3. So that is again done only from this motherboard diagram. So we saw that this red dot is undergoing simple harmonic motion, right? And it is the A sine theta component, right? And it is along the y direction. So we say at any instant the displacement is y is equal to A sine theta, correct? That's how we are getting the expression for the displacement as A sine theta. The theta can be written in terms of angular velocity and time as omega t. So you can see that omega t changing. Can you see that? With time, that omega t value is also changing. Fine, teachers. So I thought I generally do this. I always take an example of simple pendulum, draw this motherboard and teach them. I call this as motherboard. I teach them the equation of displacement. Then what do you think is velocity? How do you teach velocity? If this is
Rate of change of displacement.
displacement, so we do the differential equation. You simply
Yes, ma'am.
say
We have
dx
to
by
differentiate displacement
differentiate, you
equation.
will get the velocity.
If we differentiate velocity, we will
you
get the
your
acceleration.
acceleration and you get your equations, all three equations.
Yes, ma'am.
But to understand this, if you can make them understand this, then you can next discuss even about the phase. The initial phase, epoch, do you discuss? Do you discuss epoch? EPOCH.
Epoch.
Initial phase. Yeah, epoch. I know how, I mean, it's a very difficult word to pronounce. Like, so I pronounce it as epoch or epoch, right?
Yep.
We do discuss that, right? How do I discuss that? From this. So now here again, diagram is easier for me. So again, the circular motion, again the same. What board this is? This is motherboard for me. Everything comes from this diagram. Everything comes from this diagram. So if we can understand this and from this draw everything, it's easy. Say now, when the pendulum is oscillating, okay, I can observe it when it is at the mean position, or, so that's a pendulum. So if I can observe it at its mean position, or as it is oscillating, I may even see it when it is here, right? Or I might see it when it is here, or I might see it when it is at the other end. Correct, which means my t is 0, all right. But the object is already oscillating. Are we clear with this? I think even Vasni ma'am spoke about it when she was doing her lesson, right? So t is 0 when we start observing. When we start observing, t is 0 in our frame
Namaste,
of
ma'am.
reference.
Namaste.
Namaste, ma'am. Thank you, ma'am.
Namaste.
Namaste, ma'am.
Okay.
So now here, when t is 0, say the particle has already oscillated and it is reaching somewhere here. So again, I will go like this. Pendulum, say that is where it is. Maybe it can go up to that level. Or let me draw it in another place. So maybe it is here and maybe it can go up to this. Got me? So this is the position I am considering now. So this is where I am seeing it. So it is t is equal to 0 here. Right? This origin is the mean position. Will you agree?
Yes, ma'am.
Origin is the mean position. Now, is this particle at mean position when I am observing it? No. So where is my particle? Somewhere here. And this is the position of t is equal to 0, right? Fine.
You are considering t equal to 0 at p?
Exactly. ஏன்னா அப்பதான் நான் பாக்குறேன் அதை அது ஆசிலேட் ஆயின்னு இருக்கு நான் இப்போதான் அதை பாக்குறேன். So whenever we observe t is 0, right? Whenever we observe t is 0. That's how we always plot. Any motion when we plot generally t is equal to 0 when the observer starts seeing it. So if it has a displacement, we say at t is equal to 0, this is the displacement. Because we have started seeing it only now. So it is here. So now what it means is it's already covered an angle. Has it covered an angle? When you see it, has it covered an angle?
Yes, ma'am.
Yes. Are you clear with this? So it already has an angle covered. So for initially you wrote the equation as y is equal to a sine theta is what you wrote.
Ma'am, one doubt, ma'am.
Yes, sir.
Ma'am, after t equal to some time only we can see that point.
No. What I am trying to tell you is, நான் என்ன சொல்றேன்னா சார், அது வந்து ஆசிலேட் ஆயின்னு இருக்கு இப்படி. நான் இப்ப இங்க தான் பாக்குறேன் அதை. So எனக்கு அது இங்க இருக்கு. After
even though if you are no ma'am, if you are saying that already gone to somewhere.
Yeah, அப்பதான் நான் பாக்குறேன் அதை. நான் அப்பதான் பாக்குறேன். புரியுறதா? See, it is oscillating. It is oscillating like this. Okay, it has been oscillating. But when am I seeing it? When am I starting to see? Na, அது இங்க இருக்கும்போது. Mean positionல இருக்கும்போது கிடையாது. அது இங்க இருக்கும்போது நான் பாக்குறேன்.
For you the t equal to 0 or
at p. For me, t is equal to 0 is at p. Not for the object. For me, I am observing. So
that is the origin for you.
That is the origin of t for me. Okay. So now it has already covered some angle. From its mean position, it has already covered some angle. Will you agree? Now I am starting to see, I am seeing it, yeah. So inga irundhudu, innu konja neram kalichu inga pogum.
Yes.
So it was here. After some time, it would have gone there. So according to me, it has covered an angle theta. Are we clear?
Yes.
Okay, but already it had, from its mean position, it had covered an angle phi. Are we clear? அந்த phi-ய நான் பார்க்கல, புரியுதா? இங்க
Yes.
இருக்கு, இங்க இருக்கும்போது நான் பார்க்கறேன், திருப்பி இங்க போச்சு, இப்போவும் நான் பார்க்கறேன். So my time starts from this point, P to P dash is my time.
Yes.
It has covered an angle theta.
Okay.
Before that, it has already covered an angle phi from its mean position. Are we clear?
Yes, ma'am.
So what is the total angle that it has covered from its mean position? We always measure the angle from the mean position. So will I write this as theta or theta plus phi?
Kavya.
Yeah. So a sine theta plus phi I'll write, because this angle that you write for the sine function is always the angle from the mean position. Got me? So I will write as a sine theta plus phi. Now what I want to know is, after some time, if I move to this position, say P double dash, is that phi going to change? Are you people getting me?
Yes, ma'am.
இப்போ இங்க இருக்கும்போது நான் பார்க்கறேன், இது P dash, இது P, இது P double dash. ஓகேவா? இப்போ இந்த phi change ஆகுமா?
Phi will not change.
Phi will not change. Right?
Yes, ma'am.
Phi will not change. That phi is what we call it as
Initial.
epoch or initial phase. Right, teachers? So that's why I said, having this diagram, we can explain every possible point in the lesson oscillations as well as wave. Few I'm trying to give you. Okay. So this is initial phase. Suppose it has started elsewhere. Let me see if you can get it for me. Okay. So again, circular motion. Again, my pendulum I'm drawing here because I want pendulum's motion more than the circular motion. I'm trying to get my pendulum's motion. Okay. Say my t is equal to 0 here. In which quadrant will I place this point P? And t is equal to 0 inga irukku. So edu enoda equilibrium or mean position na idha enoda mean position. Are we clear?
Yes. For rest
Okay.
question.
Mean position, right? Now t is equal to 0 inga irukku enakku. Na inga consider pannena, where will I place the point? In the circle la na point enga place பண்ணுவேன்?
Certain angle you have to.
Where? Which quadrant? In the quadrant இதுவா எதுல place பண்ணுவேன்? So let me name it as 1, 2, 3 and 4. In the quadrant la will I place this point P?
Fourth quadrant, ma'am.
Fourth quadrant. Beautiful. Why fourth quadrant, teacher?
The zero it is
நான் இன்னும் mean position க்கு வரல. It is on the other side of the mean position. Got it?
so it's a negative angle.
Exactly. So I will place my P here. Are we clear? So that's why I said parallelly, if you do with these two diagrams, your oscillatory motion is beautifully understood. So I'll keep my P here. Okay. Then after some time, I cover some angle. Okay. I've crossed the mean position and I've come here. Okay. I've crossed the mean position and I've come here. So my P dash position is somewhere here. Are we clear, teachers?
Yes,
So
ma'am.
initially, this is my position P. Now, after some time, my position is here. So I have definitely covered an angle theta. Correct?
Correct.
I've definitely covered an angle theta. What is this angle for me? Other angle, that is phi. Got me? Beautiful. That is
Phi
Phi.
initial.
initial phase. So now if I write y, I will write as a sine. Okay, and again remember the sine function and the angle is to be measured only from the positive x-axis to that point. So how will I write it? I want only this angle. Are you getting me? What will that angle be? If I can get it from you. In the whole angle is theta. This angle is phi. What will this angle be?
Theta minus pi.
Beautiful. Theta minus
Theta
phi.
minus pi.
So do you teach your children a sine omega t plus phi or a sine omega t minus phi? Omega t is nothing but the theta. Priyarda.
Omega t minus pi.
That's all. So it depends on, so your function, your displacement equation is basically a sine omega t plus or minus phi, depending upon where you start seeing the oscillatory motion. Are we clear?
Yes, ma'am.
So the general equation for displacement is sine omega t plus or minus phi. Ide eludiyachuna, writing velocity and acceleration is not a big deal, right? You'll simply differentiate this and write your velocity. And so what I'm trying to put across here is you will thorough this part, and then it's very, very easy for you to explain the other parts in the lesson. F is proportional to minus x is where we start for the simple harmonic motion. So if is proportional to minus x, now to remove that proportionality constant, I'm going to put minus kx. Kx. So idella namak theriyum illaya. So now next what we have to do. So remember that, make the children understand the step. First simple harmonic motion. The first step that I'll write is F is equal to minus Ks, because they do need derivations also sometimes, isn't it? Just not numericals. Some of them, are dependent on the derivations for marks. So maybe we'll have to train them for that also. So F is minus Kx. Then next step, what you tell them is, either F we are writing it based on the situation that F is proportional to X and F is equal to minus Kx. But now if I bring in my Newton's second law, so 2 stands for Newton's second law. I always tell them that. Put a n next to that. 2 stands for Newton's second law. What is Newton's second law's force formula?
MA.
MA. So I think you remember the step if you can tell them this, right? Yeah, second step, say Newton's second law. F is equal to MA. Now can I compare the two and write MA is equal to minus Kx?
Yeah.
Then from that I get A is equal to minus K by M times X. Again, I've proved that A is minus X, proportional to minus X. So it is simple harmonic motion, right? Fine, teachers. So this is one step. Then in your simple harmonic motion, you would have already proved A is equal to minus omega squared X. Isn't it?
Yes, ma'am.
So comparing these two, you can get your equation for omega, and then from omega, you get your T. Then from T, you can get your F also, correct?
Yes,
So the
ma'am.
step that I make them remember is this. Any example you do for simple harmonic motion, first write the step F is equal to minus K times the displacement. Second, you bring in your Newton's second law and write this equation. Compare the two, get your acceleration expression. Third point, know that for simple harmonic motion, simple harmonic 3, right? SHM, right? So some short forms I try to make my children remember the steps. So SHM, simple harmonic 3-letter word. So step 3 is A is equal to minus omega squared X. Then I ask them to compare the two steps and ask them to get the expression for omega, which is root of K by M. Then we know T is 2 pi by omega. Get the frequency and time period. Is that fine, people? So these are the steps that we'll remember for any derivation of simple harmonic motion, namely spring mass system and simple pendulum. Right? So I don't think I'll go through the derivations. So these PPTs I will share with you, which helps you to understand. You can just go through these diagrams. It beautiful. See again, see the mother diagram is given here. You can see that I call that as motherboard diagram. Okay.
Okay.
So you can very beautifully understand. See, I've applied a force and got it to X is equal to A. So where is my T is equal to 0? My T is equal to 0 there. Are we clear?
Okay,
And we are
ma'am.
going in this, and we are going in this direction. So if you can just compare this with this. So I'm at the maximum X equal to A. My force is in this direction. Amplitude is maximum. See the acceleration direction. So if you can just use these diagrams, and you understand it, you will be able to beautifully put it across to your children. So I just leave this to you. Okay, you can just go through it, and if you have any doubts, you can get back to me. Will that be fine? Because we are
Okay.
running short of time. Otherwise, I would love doing everything, but
Okay.
then we have to finish everything in this stipulated time. So I thought I'll just run it through. Then, of course, coming to our energy. Right now, energy is, you know, the total energy is kinetic energy and potential energy. How do we get this expression for potential energy? How do we do that? So that's the next thing that children, you know. Yeah, so what is energy basically? Energy basically is force into
distance.
force into
Distance.
displacement. So we will come to the
Displacement. Work done.
yeah,
It's
F,
equal.
work done. Exactly. Potential energy means work done. Correct? Potential energy means work done. Okay, in moving it from this position to that position, right? So force into displacement. Fine. What is the force involved here? This is a simple
Spring
harmonic
force.
motion.
Spring
So
force.
spring force, na, it is a restoring force. Are you getting this?
Yes,
Or the
ma'am.
force applied. You can derive it in two ways. Either you do the applied force, or you can use the spring force. Any one you're going to use and do it, because there's a very important graph in your textbook which you have to beautifully understand and tell the children the difference between the graph between F and X when it is applied force and F and X when it is a restoring force. So quickly, if I can get that for you, 1 second. Suppose I draw, now this you are talking about spring mass system, isn't it? Suppose I draw a graph between the applied force and extension. This comes, of course, in your work per energy, but I thought I'll just touch upon that here. So if I draw a graph between force and displacement, what kind of graph will I get? This is simple harmonic motion where F is proportional to X. So what kind of graph will I get? Anything proportional, X proportional.
Straight line.
I'll get
Straight line.
So I'll get a straight line in this quadrant, right? Suppose I draw a graph between restoring force and X. In which quadrant do you think you'll get the graph?
Third quadrant.
Negatives.
Why third quadrant? Will it be third quadrant or just think and tell me? See, restoring force is F is positive, X is. If F is positive, if you take F as positive,
Second.
X should be negative, right?
Negative, ma'am.
So in which
Second
quadrant will it be? Are you getting me? If you draw it in the third quadrant, it is still applied force versus X. So this whole line, blue line that I've drawn now is F proportional to X for F applied. Okay. If I say restoring force, in which quadrant are you going to get that? You're going to get in this quadrant. Got it? Why? If F is positive, X is negative. And if F is negative, X is going to be positive. Are we clear with this? See, if F is positive, X will be negative. This is my restoring force. Are we clear? So this blue line will be for F applied. And this red line will be for F restoring. Right? So that is one thing, like whatever comes to my mind as I'm teaching, I do try to bring it in here. Okay. So now coming back to a simple harmonic motion, force into displacement. So force is Kx, right? Displacement is dx. Don't write it as x and say kx squared. Why can't you say that? Why do you think you can't say that? You can't, it is half kx squared, Vardelia. How do we get that? See, this kx has to be taken at one particular point for a very small displacement where you can consider the force to be k times x. And if you want to displace it from x is equal to 0 to x is equal to a, I'll have to integrate this. Integrate it between what limits? From 0. Got me? If it is a, I'll put it as a. But we take it as x. So now if you integrate kx dx, k comes out, x dx is x squared by 2, and that is how we are getting the expression half
Integral
kx.
of x into ds, x squared by 2.
That's all. So you get half kx squared. So that is the expression for potential energy. Fine. And of course, for getting for kinetic energy, you go substitute for V, isn't it? Expression is half mv squared, all right. And I think you do know the derivation that V is equal to what, people? V squared is equal to, tell me, do you do that? What, people? V is equal to a cos omega t, and now y is equal to a sin omega t. V will be a cos omega t. A cos omega cos omega t can be written as 1 minus sin squared omega t. So from that you will get a squared minus y squared. Omega into a squared minus y squared. You go substitute it in V, you're going to get your kinetic energy expression. I'm not going into go into all those things. Then finally, see, that is what is given here, V as plus or minus omega into a squared minus x squared. Then you go substitute it, you're going to get your total energy. What I am interested again now is this. I'll just stop sharing this. Right now, after discussing your energy and all that, one more graph that we will be discussing here. So do we have to do this graph? Y is equal to a sin omega t. See, it's a sine function, so automatically sine curve. And V is equal to a cos omega t, so it will be a cos curve. Right, let me draw it properly. I think this graph is ulta of what is there in the textbook, because in the textbook he has taken x as a cos omega t. So don't confuse between the two figures. This is y is equal to a sin omega t, right? If I had time, I would have actually drawn this also, but then we are everything has moved. God knows how it has moved. So quickly, y, v, and a. So y is a sine curve because it is y is a sin omega t. I'm just taking for omega t, taking the initial phase to be 0. Then for v, I know is dy by dt, so it will become a omega cos omega t. So this will be a cos function. Very difficult to draw if you don't draw the axis. Yes. That's how you'll get it. And this will be the ulta of this curve. I think this, you know, it's there in the textbook, right? So I'll just put a proper curve and give you, but then this is what it is going to represent like. Now, why did I take this graph is, what is the phase difference? Now we have to talk about phase difference between displacement, velocity, and acceleration here. So what do you think is the phase difference? How do you explain to the children the phase difference? Because children do get a little confused. The way you have to understand, see, this is at 0, right? But this one is at the positive peak already when this is at 0. That means it is like this has crossed 0 and come to the positive peak already. Are we clear? So which is ahead, V or Y? Are you people getting me? V is ahead because it has reached. That is the way you must make the children understand. V is at the positive peak. Y is still at 0. Because in a thing, if you see, first I start from 0, then go to the maximum positive value, then come back to 0, then go to the negative value, and then come back to 0, right? So if you see, V is already at the positive peak when Y is still at 0. So which is ahead of which? V is ahead of Y. Now, likewise, what can you say about acceleration when you compare it with velocity? Acceleration வந்து இது ஃபுல்லா முடிச்சிருச்சு. That's the way you should make the children understand. Fulla mudichittu, it is starting here. So it is starting to come down. That means it's already finished this part. Are we clear? So acceleration is ahead of velocity. Either ahead of velocity, okay, by what angle na? So again, I'll go back to my motherboard. Again, where will I go? I'll go back to my motherboard. What does my motherboard say?
Sine angle.
Hello, what does my motherboard says again? I draw this motherboard again by the side. Okay. Sin omega t na inga arambipen. Cos omega t na inga arambipen. So what is the angle? 90. Are you getting it? 90. So what is the phase difference between V and Y, Adina? It is 90.
90.
Similarly, between V and A na? Between V and A na? Is it 90 or 180? What is it?
V and A means 9.
See, இது இங்க இருக்கு. V இங்க இருக்கு. See, இங்க Y இங்க இருக்கு. V இங்க இருக்கு. A இங்க இருக்கு. புரியுதா? Just an idea. If Y is at the mean position, sine curve, V is the cos curve, it starts here. A is sine curve, all right, but it is ulta, isn't it? So it has to start from the negative value, correct? It has to go in the negative. So it should be where? Somewhere here. Are you getting the idea? So A is ahead of V by 90 degrees. Are we clear with this? Because we go only this way. So V is ahead of Y by 90. A is ahead of V by 90. That means A is ahead of Y by 180 degree. So I always, that's why I said throughout this chapter, I try to always draw this circle and make them understand whatever I want them to understand. So understanding the circle is very, very important for you. If you can analyze all this and go to the class, you will be able to put the chapter very beautifully across to the children. So is that fine, people? So far? Okay, and either like, when you do wave displacement equation is going to be the same, A sin omega t or A cos omega t, correct? Displacement equation is going to be the same. Then when you are going to talk about the phase difference between two waves, upon phase difference between two waves and when you are talking, don't talk about Y, V, A. So what I do is I do this. So I'm just trying to share whatever I do and find it useful. Hopefully you find it useful. So now here, when I'm talking about two waves, all right, wave motion, when I'm talking about two waves, so again I draw the motherboard. Okay, and I say one particle is here. What is the equation I'll write if the particle starts here? What is the equation, teachers?
A sin omega.
A sin omega t is what I will write. Suppose it starts here. My t is equal to 0 starts here. What is the equation that I will write for that Y? So I'll call this as Y1. Okay, well, this is for particle P1. Okay, or this is a wave P1. There's another one which is here. So what will I write Y2 as? Can I write it as A sin omega t plus pi by 2?
Yes, ma'am.
It's gone ahead by a pi by 2, correct? In the inge anga ponale pi by 2 dane.
Yes, ma'am.
Right? So what is the phase difference? These two?
90 degree, ma'am.
90 degree. So that's why I say always take this circle and draw, you will be able to connect it. Any other ideas that you have when you teach this phase difference between two waves or two particles? Anything else you do, teachers? I find this very useful for my children. Do you have any other ideas that you do? What teachers? And I always see, and when they find it, so suppose either kudukala rendu equation kuduthirukenu vechupom. Okay, these are the two equations given. Okay. And they are asked to find the phase difference between the two particles or two waves. What should you said now? Pi by 2, right? Which is ahead of which one? In the diagram, okay, wow. So suppose I'm giving these two equations. How do I know which one is ahead of which one? I always ask them to stick to y2 minus y1. Or instead of doing y2 minus y1, I call this whole thing as some theta 2, and this omega t, whatever is there for the sine function here as theta 1. And I tell them always find out theta 2 minus theta 1. Don't change this order. Then children are never confused. This is what I have experienced. So theta 2 minus theta 1. Now this theta 2 minus theta 1. Tell me what is theta 2 minus theta 1 here. Theta 2 in the omega t plus pi by 2 together is called theta 2. Got it? And omega t there is called as theta 1. So what is theta 2 minus theta 1 mathematically? I'll get plus pi by 2.
Yes, ma'am.
All are ending towards the session, so all are feeling tired, is it? We have 10 more minutes still, teachers. Yeah, theta 2 minus theta 1 is
pi by 2.
plus pi by 2, correct?
A sin by 2.
No, leave out
Yes,
A
ma'am.
and all. See, phase difference when you're finding phase difference between two particles or phase difference between two waves, don't be bothered about all this. Especially if it is the same function, A sine, I don't have to be bothered about this A sine. Got it? I will take what is there within the bracket for that sine function. What is there? Omega t plus pi by 2. Omega t. So what I'll do is I'll always do this order, theta 2 minus theta 1. So it is actually omega t plus pi by 2 minus omega t, correct? So this omega t and omega t will get cancelled. What I have is pi by 2. But I have plus pi by 2. So immediately what I'll say is, if I get a plus sign when I subtract, then the second one is ahead of the first one. Other than in the diagram. So namak in the diagram, we can easily understand this and make the children understand. Suppose my theta 2 minus theta 1 comes to be negative, then the second wave is behind the first wave, or the second particle is behind the first particle. Will this be useful when you teach? Yeah, some basics is what we are trying to, because we have to understand these basics, because next when I come into the next chapter that I want to come into you for is in the 12th standard wave optics. So on the wave optics, I'll touch some more about the superposition principles of the waves. For that, all these basics are very much essential. So I thought I'll touch upon the basics here of waves. And when I come into wave optics, there 1.5 hours, there I will touch upon the other parts that I want to touch in wave motion. Will that be fine, teachers? So and of course, in the waves, when I go to the wave chapter, there is transverse wave, there is longitudinal wave. I think all that is fine. You can easily teach them that transverse wave and longitudinal wave. Can you? Yes or no? So I have some nice gifs for you. I have some nice gifs for you here. So this is again one thing that I really liked. So I thought I must share it with you. See, I'm having this. You can see the two projections there, teachers. I taught you with one projection, correct? Red dot matra I taught you.
Yes.
Or I discussed with you. I shouldn't say I mean, I'm getting my children's idea, then I'm telling I taught you. Right. But see here, I'm showing you even the blue dot. What is that blue dot? That's the X projection. What we saw is Y projection. So you can, that's why I said you can resolve the position vector into two, one horizontal, one vertical, and talk about any one. If I talk about the vertical, it is the red dot. If I talk about the horizontal, it is the blue dot. But both you can see they are undergoing simple harmonic motion. Can you see that? So if you have some kind of a digiboard or something in your class, you can show this, or you can draw it and show. Yes or no? You can beautifully draw this and show. So one will be sine. So one, the displacement will be sine. For the other, the displacement will be a cosine function, cos function. Other base funny, you can make them draw. You can give them as an assignment. Make them draw the velocity and the acceleration graph, so that they will understand how exactly the three quantities are varying in the phase. Then there's one more that I wanted to show. This is a very nice GIF that I got when I was just going through. And can you see what can you see about the particles? I'm sharing, right? So you can see the particles of that water molecules, isn't it? What do you
Yes,
see
ma'am.
there? What do you see there, teachers?
Up and down.
Vibration.
Verum up and down, or is it also moving sideways?
Moving sideways.
Moving
Sideways also, and you can see
Beautiful
that
GIF, Miss Radha ma'am. Beautiful GIF.
Yeah, I
Beautiful.
thought it was, it's very interesting when I went through the GIF. Actually, these are representing the wave motion on the surface of a liquid. You can see hardly all the molecules down moving. Does it move? Hardly they are moving. You can see that because here itself the circle is a very small circle, not much. See, again, this is a motherboard. You're having both the transverse wave and the longitudinal part in this wave motion, actually speaking. And if you go down, you can see that transverse is not happening. Hardly it is happening. You can only see the particles moving a little this way and that way. And we do understand transverse waves do not travel well inside the liquid, because transverse waves need cohesion for their traveling. Cohesion is a very important property for them to get propagated. So maybe all this we can discuss a little on that day when I do wave optics, a little more about the waves we can discuss there. Okay. And one last thing that I wanted to do here is just maybe one problem on, because 1.5 hours is definitely not kind of enough to discuss both. So of course, this is not the end of all, teachers. If you feel you should discuss some more about the chapters, you can always, get in touch with us, and then we'll be able to help you with that. And you have some beautiful ideas, please do share it with us. Because as I told you last time when we were handling 9th and 10th physics, I got a lot of ideas from you teachers. It was a wonderful session actually. So now here, one thing that I wanted to discuss is, like, if you have an equation, so let me start drawing. So this is one thing that we will be even using in our 12th standard in EM waves. When we are talking about all the types of waves we do, isn't it? All the types of waves, plain progressive wave, we'll be writing it like that. A sine, right, omega t plus or minus kx. Am I right?
Yes.
Am I right, teachers?
Yes,
When we are
ma'am.
doing a plain progressive wave, we don't just stop with omega t, because the wave is moving, we get it, the wave is going to, the particles thing is going to change with respect to displacement, is going to change with respect to time, as well as it's going to be different with respect to position. So we are going to write the equation as a sine omega t plus or minus kx. If a plus kx vanda wave eppadi move ஆகுது, minus kx vanda wave eppadi move ஆகுது. Because the wave can move from left to right or right to left. These are the two directions that we generally practically consider, left to right or right to left. So if I'm given an equation like this, will I write plus kx for left to right or minus kx for left to right? That is the next question. We have to understand this. Teachers. So I'll tell you.
Plus kx left to right, ma'am.
No, it's minus kx for left to right and plus kx for right to left. Very important point that we have to remember, because in your 11th exercise itself, you go see, they would have given one equation with values for omega, k, everything. And they would have asked you to identify whether the wave is a stationary wave or is it a progressive wave. If it is a progressive wave, is it moving from, in which direction is it moving? Is it moving from left to right or right to left? So very important, and the same equation will again come back to you. If you have done 12th, you will agree with me. It will come in EM waves. They'll give you an equation for electric field, or magnetic field and ask you to find out the rest. So in that case also you will be getting a function like this. So a sine omega t minus kx or kx minus omega t. Either way you can write it. No harm, because your textbook would say write it this way. Unga textbook la poi pathina, it would have written as kx minus omega t. Both are fine, people. Don't say, ma'am, one minus sign has to be pulled out from this to make it kx minus omega t. No, it depends on how you draw the sine curve. If you draw it this way, it's still these two are still traveling left to right only. Okay. If you draw it this way, it will be omega t minus kx. You draw it this way, it will be kx minus omega t. Okay. So no harm in writing kx minus omega t or omega t minus kx. But what we have to understand it is, if this minus sign is coming in between, it's a wave traveling from left to right. And if it is a plus kx coming, then it is a wave traveling from right to left. And these two is what you combine and use the superposition principle to find the equation for a stationary wave. So all these basics, if we understand, then the wave equation or the wave lesson becomes very, very easy and simple.